Okay, so we're going to continue where we left off in the last lecture. And so we're talking about, remember, different types of paths through graphs, or understanding paths and circuits through graphs. And last time we talked about Euler circuits. And so remember, an Euler circuit is a circuit that goes through a simple graph that crosses, which could be a multigraph, right? It's allowed to be a multigraph. But the circuit has to cross every edge on the graph exactly once, right? So there can't be an edge that is missed, and there also can't be an edge that you cross more than once. And we had the following theorem, which we proved last time, which was, so suppose you have a simple multigraph, which is connected. I mean, remember, why does it need to be connected? If it's disconnected, it doesn't make sense to talk about a circuit through the whole graph. If you look at the connected components, and if it's disconnected, the theorem will apply to those components if you want a circuit in one of the pieces. Right, and so the theorem is, if you have a graph with these assumptions, then G has an Euler circuit if and only if, meaning equivalently, every vertex has even degree. Right, and so, so the hard direction of this theorem, so remember, when you see an if and only if statement, it means that the two claims are equivalent, meaning they're either both true or both false. So this theorem says two things. It says if G has an Euler circuit, then necessarily every vertex has to have even degree. And it also says that if you assume, or if you know that every vertex has even degree, then you can always find an Euler circuit. Right, so notice that those two statements are logically different statements, right? They're two different implications. And so they're what are called converses of one another, right? And so it's not necessarily true that if a statement is true, then the converse is also true. But this is an example where both are true. Right, and so remember, the hard direction of this proof was the direction where if you assume every vertex has an even degree, then the graph has to have you can always find an Euler circuit, and we talked about an algorithm which you can do, which makes this work. And so remember, last time we also introduced, when I defined Euler circuits, we introduced Euler paths, which are not paths. I mean, every circuit is a path, but let's talk about Euler paths, which are not circuits. And so remember, what is an Euler path? It's just right, so instead of having a circuit, it's just a path through G that hits every edge exactly once. The important point is that it hits every edge, and it doesn't cross any edge more than once. And so you may wonder, well, we have this theorem for circuits that characterizes when you can have an Euler circuit in a graph. And so the question is, well, is there a similar theorem for Euler paths? And it turns out that this is the case. And so let's suppose that G has the same hypotheses as above, meaning it's a simple multigraph and connected. And so the theorem is that G has an Euler path, meaning a path that goes through every single edge exactly once on the graph, if and only if there are exactly two vertices in G of odd degree. So that means there's two vertices of odd degree, and every other vertex has even degree. Right. So there are only two vertices which can have odd degree, and you need exactly two. Right. And so I'm not going to go through the full rigorous proof of this, but the idea I can draw in a picture right here. So it's going to actually basically be a consequence of the previous theorem about Euler circuits. And so let's suppose that V and U are the two vertices in my graph that have odd degree. Right, so for this picture, let's just suppose they have degree 1. So there's the same idea will work if they have degree 3 or degree 5 and so on. So there's some edge leaving V and some edge leaving U that connects to the larger graph G. So I'll just block this off and say this is the rest of G. Well, how are you going to find an Euler path in this graph using the previous theorem? Well, what you can do is artificially add a new edge, right? Call it E bar, right? So add a new edge E bar. Well, since this edge increases the degree of V and U by exactly 1, the new graph, every vertex in the new graph now has even degree. Right? And well, if every graph in the, if every vertex in this modified graph has even degree, I can apply the previous theorem to find an Euler circuit using the algorithm we talked about last time. And then, well, what happens if once I have this circuit? Well, if this circuit crosses through every single edge in the graph exactly once, including E bar, including this artificial edge which I've added, but then I can just delete E bar from the circuit to get a path, right? So delete E bar to get path, and you'll have an Euler path, right? And this also gives you an algorithmic way of finding a path. The first thing you want to do is isolate the two vertices that you know have odd degree, and then connect them by a new edge E bar, and then you'll have a graph to which you can apply the algorithm we talked about last time to find a circuit, and then you just remove the part of the circuit that crosses from V to U over E bar, and that will give you path. And so that's the harder part of the proof. The other part you can right. So we prove that this basically proves that if there are exactly two vertices of odd degree, you can always find an Euler path. You also have to prove that if there's an Euler path, then all the vertices except for 2 have even degree, and then the other 2 have odd degree. And so you can do that using a similar argument to what we saw in the easier part of the proof of the first theorem. So I'm going to skip over that for today. Great. Okay. And so that's about everything I want to say about Euler paths and circuits for now. So there's another notion which is very similar, although it turns out is a little bit more complicated, which is the idea of something called a Hamiltonian path, named after another mathematician, Hamilton, from I think the 1700s as well. Right, and so what is the Hamiltonian path? So it's very similar. So it's going to be, or sorry, let me modify this. We want paths and circuits. Right, and so a Hamiltonian path through a graph or a circuit, well, it's going to be a simple path or a circuit through a graph G that passes not through every edge exactly once, but every vertex exactly once. So this is the main difference, right? Euler paths, you want to hit every edge. Hamiltonian paths, you want to hit every vertex exactly once. And so, I mean, where do these things arise? They arise in a variety of contexts. So one thing that's worth pointing out is that these types of paths are related to a famous problem in computer science and math, which is called the traveling salesman problem, which we'll talk about a little bit more maybe later this week. And so the problem is the following. So let's say you have a bunch of towns. Right, so some different towns that are connected by roads, say town A, B, C, and D, and you want to find the shortest path that hits every city. So there's some salesperson who's traveling around and trying to sell to different, like, insurance or whatever in different towns, and they have to hit every single city in the day. But they want to optimize it so they're not traveling to the same city more than once. So what's the shortest path that goes through every town exactly once? Right. Right, and so this turns out in general to be a very hard problem to solve algorithmically. So we'll have a little bit more to say about this once we talk about some simpler graph path finding algorithms in later today and in the next lecture. But just so you know, like when you hear about this traveling salesman problem, it's really asking for a Hamiltonian circuit in a particular graph, and that's what it's about, right? So this is one example. Right, and so one example where this arises outside of just some sort of like simple pictures, but maybe let's also look at some simple pictures. Right, so let's suppose my graph looks something like this. Right, suppose this is G. Well, let's try to find what is an example of a Hamiltonian path through this graph. Well, I want to start at some point, and I want to hit every single vertex, right? So maybe I can start here, and then go from here to here, and then from here to here, and then from this vertex to the last, right? So this is a Hamiltonian path. Right, sorry. Okay, right, so that's an example of a Hamiltonian path, and let's look at another picture. So let's say the graph H is the graph where right, so let's say H is this graph. Is it possible to find a Hamiltonian path through this graph? Well, once again, we can try to just guess and check and work our way through. So one thing you can try is, well, let me go from here to here, and then cross through to go to this vertex, and then zigzag along to this one, and then finally I can go down and hit the last vertex, right? So this is an example of Hamiltonian paths. And so notice that we don't have to hit every single edge, right? Because in each example that I did here, we did not cross through every edge. So these are not Euler paths, right? So it's possible to have a Hamiltonian path that misses a lot of edges and therefore is not an Euler path. Right? Okay, and so you may ask, is there a theorem similar to what we had for Euler paths where that basically characterizes when it's possible to find a Hamiltonian path and maybe even tells you how to do it? So well, it turns out that there's no simple theorem like we saw for Euler paths, right? I mean, the proof of the theorem for Euler circuits was not a simple proof, but the statement is at least simple, right? You have a very clear criteria to check, which is just, does every vertex have even degree? If not, are there only two vertices of odd degree, right? It turns out that there's nothing like this for Hamiltonian paths. Right, so there's no simple criteria for determining if a graph G has a Hamiltonian path. Or circuit, right? I mean, these problems are sort of equivalent because you can artificially add things. Yeah. Right. So again, the main point is there's no sort of compact, straightforward theorem that will characterize when this is possible. But that doesn't mean that you can't, in certain cases, at least rule out the existence of a Hamiltonian circuit or path. Like there's always a few criteria you can look for to help you try to understand this problem better. So let's just look at some of these criteria quickly. Well, the first thing to point out is that if, let's suppose your graph G has a vertex of degree 1. Right, so what does that look like? Well, maybe I have this vertex B here, and then I have the rest of the graph, right? right? So the rest of the graph is over here. Well, in this case, you can't have a Hamiltonian circuit, right? It's possible you may have a path, but you at least can't have a Hamiltonian circuit. And why is this? Well, let's suppose the path leaves the graph and goes here. Well, then it can't go any further, right? So where is it going to go if the degree is only 1? And similarly, well, let's suppose you start at V. Well, if you start at V, you eventually have to come back. But as soon as you come back, you're gonna have to cross through this vertex again, right? The one vertex that's connected to V. And so, right, so this is one simple criteria which at least rules out having a Hamiltonian path, right? If there's a vertex of degree 1, there's no Hamiltonian path. Another slightly more complicated criteria. Well, one thing to point out is that if G has a Hamiltonian path, which I'll just abbreviate with H, like say, excuse me, you have to be careful here. So I mean Hamiltonian circuit. Then, well, every vertex has to have degree bigger than or equal to 2, right? Basically by the last statement, right? Right. Sorry. Just pausing for a second. Right. Sorry. So I was just trying to think of how to phrase the next example. I think it's better to just look at it as an example without trying to write down a general principle, and you'll see how to like make this principle work for more complicated graphs. So let's look at a particular graph, and what we're going to do is show that this graph does not have a Hamiltonian path. Right. So let's say the first, I label the vertices like this. And so I'm going to claim that this has no Hamiltonian path. Right, and so why is this the case? Well, look at the vertex C. Right, so if I have, let's imagine I had a path going through this vertex C. Let's suppose this path happens to travel from B to C to D, right? Well, as soon as the path travels from B to C to D, it's not going to be able to travel through the edge connecting A to C and also the edge connecting C to E, right? Why is that? Because if it does, it would have to touch C more than once, right? So the path can't travel through these, assuming it goes through the blue part. Right, but then that's an issue because let's, for example, suppose it happens in this way, then I go from B to C to D, I have to travel from D to E. But as soon as I travel from D to E, there's a problem because I can't go back to hit A, right? Right, so if you have like a crossing like this, you can often look at that crossing and analyze it a little bit as I did and use that to rule out the existence of a Hamiltonian path, right? Right, so in particular, as soon as the path crosses through a particular vertex, you need to delete, you have to remove from consideration all other edges incident with that vertex, right? So let me just put that as a side note. Right? So as soon as you have a Hamiltonian circuit or path crosses through some vertex, say V, you need to remove all other edges that are incident with V, which were not traveled by the path initially from consideration. Right? Right, so when I say all other edges, I mean all other edges incident with V that were not already, right? So there's going to be two that were already crossed, right? When the path crosses through V, there may be some other number of edges that connect from V to other vertices, while the path can't travel through those vertices because then it would have to cross through V more than once, right? Right. Okay, and so, right, so this is the sort of analysis, the basic analysis you can do to at least detect if a graph is not Hamiltonian. There are more complicated theorems which allow you to check in general if it is Hamiltonian. So one example is this is something called Ors Theorem, or maybe it's Orea, I'm not sure, which is the following. So if you have a simple graph and you have n vertices on the graph, let's suppose n is bigger than or equal to 3, well, this gives us a criteria for when the graph will have a Hamiltonian circuit, and the criteria is the following. So suppose that for all non-adjacent pairs, meaning they're not connected by an edge, of vertices uv, right? So let's say G is given by vertex set E and vertex set V and edge set E. If for all non-adjacent pairs, the sum of the degree of U plus degree of V is bigger than or equal to N, right? So the cardinality of the vertex set is N in this case. Then in this case, G has a Hamiltonian path, or sorry, circuit. I keep mixing these up. Right, so this is at least one criteria, which is much more complicated than in the setting of Euler circuits. In Euler circuits, it's just about whether or not the vertices have even or odd degree. This requires a more, which is sort of a local thing, which you just look at each vertex individually. This involves some more complicated interactions between the different vertices, which are in particular not adjacent to one another. And so what I'm going to do, I'm not going to prove this in the lecture, but I will send you a handout with the proof of this theorem so you can read if you're interested. It's actually, the proof is actually outlined as an odd exercise in the corresponding chapter in the textbook. I think it's a little cheap to just defer it to the exercises, so I'll write out the proof for you, and you'll at least see an example of how this works if you're interested. Okay, and so, right, so since Hamiltonian paths are much more complicated than Euler paths, there's not much more we can say beyond these simple examples. So I'm going to move on to talking about a different type of path problem, finding problem. And so we're now moving on to section 2 or 10.6 in the textbook. And so this is all about weighted graphs and shortest path problems. Right, so we'll still be talking about paths through graphs, but in maybe a slightly different way. Right, and so what is a weighted graph? Well, there are a few ways to define weighted graphs. The manner in which the type of weighted graph that we're going to talk about now are graphs where you have certain weights on each of the edges, which say maybe take into account some cost to travel along the edge, right? And so what's an example of something like this? So we can look at, for example, a flight cost graph. Right, and so let's suppose we have, I'm going to write down some collection of cities, and the edge will connect one city to another if there's a flight from that city from the first city to the second. And I'm also going to attach a number to the edge, which will estimate the price of flying along that path, right? So maybe I have here, San Francisco and LA. Maybe there's a flight between those that costs $100. I know that these prices are not going to be completely accurate. So maybe you have Chicago out here, and then Boston over here, New York over here, and Atlanta over here. And let's just include some edges, right? So LA to Atlanta, let's say that's 350, and so on. So let me just copy this over. Right, so maybe there's, right, so maybe you can get from San Francisco to New York by first doing a layover in Chicago and then flying from Chicago to New York, or you can take a direct flight from San Francisco to New York. Let's say that's 600, right, and so on. So let me finally, sorry, in order to have interesting examples, I have to pause a lot of time to like copy over. So it's going to eat up some dead air time. Right, so this is an example of a weighted graph where, again, each edge denotes a flight from the first city to the second, and on the edge I have the cost of the flight. And so what is the general problem associated with these types of graphs? Well, I want to find a path from one point to another with minimal cost, right? So I want to find a path from point A or vertex A to point Z or vertex Z with shortest length or minimal cost. Right? And so how do we measure the length or the cost of a path? Well, you just add up the numbers of the associated to the edges that you travel, right? So for example, let's say we wanted to find the shortest path from Boston to LA. Well, if you inspect the graph, you can see that if I travel from Boston to Atlanta, this costs 180. And then if I take the flight from Atlanta to LA, that costs 350. And so the total cost in this case, if I add these up, is $530, right? So it costs $530. Well, you can check that if you look at other paths, then every other path is going to cost strictly more, right? For example, so this turns out to be optimal in this picture, right? And so, for example, if you look at just as an aside, if let's say I did Boston to Chicago, and then did Chicago to LA, well, how much does that cost? That costs 200 from Boston to Chicago, and then 450, right? So that's going to be 650, right? And there are a few other options you can try, and you can, unless I made a mistake here, you can check that they're all going to be smaller than the first choice, right? And so now, okay, so how did I actually solve this problem? Well, I just looked at the graph and I enumerated the possibilities, and I just saw by guess and check basically that the first option I picked is the optimal choice, right? So this is the optimal route according to the prices listed in this graph. In general, you're not going to be able to solve this problem just by guessing and checking, right? And especially, okay, this graph has 6 different vertices. Like, what if your graph has 20 different vertices or something like that? Then the number of edges is going to be very large, and it's going to be virtually impossible to solve this shortest path problem just by inspecting the graph and trying to guess. And so what you have to do is develop a more sophisticated algorithm that isn't just like brute force guessing. And this is the next thing we're going to spend a little bit of time talking about, is how to solve this problem in general without just brute forcing and guessing. Great. Right. And so the main algorithm we're going to talk about is an algorithm due to I think Norwegian mathematician by the name of Dijkstra, who I'm going to repeatedly have trouble pronouncing his name. Right, and so I think Dijkstra was probably the first mathematician slash computer scientist to like give a full solution to the problem we just talked about, where you have like a relatively efficient algorithm given a graph with weights on the edges to find the shortest path from point A to point B. And so what I'm going to do, I'm going to break up the description of this algorithm into the rest of today's lecture and also the following lecture, because it is worth spending some time talking about in detail. And so today we're just going to look at it at an example where I don't really write out the whole algorithm, but just go through the idea for one particular example. And then next time I'll write out precisely what the algorithm actually is. Right, and so let's look at well, what is the main idea of the algorithm before we look at an example? Right, so the general problem is we're trying to find the shortest path from one point to another, where again, I'm putting shortest path in quotes because I really mean like the path with the smallest cost when you add up all the numbers on the edges, which may not actually be the shortest length path. It may have a longer length in terms of number of edges, but it just so happens that when you add up the weights, then it's the smallest. Right, so say from A to Z in a graph G. Well, one thing to point out is, well, let's say A is over here and Z is over here. And let's say I travel in some path starting at A. Right, so there's some large portion of the graph which I'm not writing, which you can just imagine is between these two brackets. Right. Well, eventually it's going to leave this, and there's going to be some different vertices which are connected to Z. And so the shortest path from A to Z has to pass through some other vertices, right? Unless A is directly connected to Z. And even then, it may not. Right. So this is an aside. Like let's suppose I had an edge from A to Z, and that's it. And I know that A and Z are connected. This doesn't necessarily imply that I know how to solve the problem, right? Because maybe the edge from A to Z has weight 1,000, but then maybe there's like C, D, and E, which have like weight 10, right? And so I can get from A to Z either by traveling directly, which would cost me 1,000, or by traveling this other route, which would only cost me 40, right? So just because A happens to maybe be connected to Z, it doesn't necessarily imply you have a solution to the problem, right? I just wanted to point that out. But one thing that you do know is that, let's suppose I do have the shortest path. Let's suppose these 3 points, I'll call them x1, x2, and x3. Right, so the shortest path from A to Z, well, it's actually the same as finding the shortest path from A to some other vertex that's connected to Z. Right, where xi is incident with Z, right? So there's some sense in which this algorithm, whatever algorithm's going to work, there's like simpler versions of the problem built into the larger problem you're trying to solve, right? So the problem of finding the shortest path from A to Z turns out to be the same as first finding the shortest path from A to some other vertex which is connected to Z, and then also keeping track of, well, of those, which of the three is the smallest, right? So finding the shortest path from A to Z is the same as finding the shortest path from A to a different vertex, and then the shortest path from that vertex to Z, taking into account all the possibilities, right? And so this is the algorithm we're going to talk about is an example of a principle which you may have heard of in a programming or computer science class called dynamic programming. Right, so this algorithm will be an example of dynamic programming. Great. Okay, and so let's go through a particular example, and then in the next lecture, I'll talk about again more precisely how the algorithm works in general. And so let me copy over a picture here. So let's look at the following graph. With these weights, which I'm labeling now. Right, and so what we want to do is find the shortest path from A to Z, meaning taking into account the weights. Right? Right. Okay, and so there's a relatively few number of vertices and edges here. So if you just list out all the possibilities which you can do, you'll be able to find the answer, right? And so it turns out in this case, the answer is, well, if you go A to C to Z, that'll contribute the smallest cost. So that'll be the answer. But what we want to do is try to approach this problem using a method that will generalize to more complicated graphs, right? And so this is a good principle to keep in mind whenever you're trying to solve a new problem or maybe work on a new algorithm to solve a problem, is you want to look at simple cases which you can probably understand using different methods, but then use the simple picture to help you like write out an algorithm that will work in a more complicated setting, right? And usually, like if your example has like relatively large number but not too many number of vertices, for example, for a graph, some of the ideas that you have about finding the shortest path will generalize, and so you want to keep those in mind. Right, and so that's what we'll do now. And so, right, so how are we going to do this? Well, I'm going to break it up into several steps. And at each step, I'm going to try to keep track of the shortest paths from A to other vertices. Although we have to do this in a clever way, which is what which is gonna be the main point of the example. One thing I want to point out though, before we go into more detail, just related to what I was saying before, is notice that if we're going to find the shortest path from A to Z, well, then that path is either going to go from C to Z or from D to Z, right? It either has to cross through D or C. And so therefore, the problem is going to require us to understand the shortest path from A to D and also the shortest path from A to C. And then with that knowledge at hand, compare the shortest way to get to Z from those 2 points, right? And so we really have to, in our algorithm, we have to build in smaller subversions of this problem, which include not just the shortest path from A to Z, but also the shortest path from A to D and from A to C, right? And so this is another example of this dynamic programming principle, which sort of drives this algorithm, right? And so what are we going to do? So step one, well, I'm gonna pick a set of vertices, which I'll keep adding to. And so I'll begin by setting my set just equal to the vertex A. And what I now want to do is label the vertices connected to A in terms of their distance to A, meaning the distance in terms of the weights, right? When we're talking about weighted graphs, distance no longer means the number of edges, it means you sum up the weights on the edges to get from one point to another. So in terms of the shortest distance to A. Right, so for example, I'm gonna label B as 2, and I'll label C as 3, right, because I have a path from A to B of length 2, right, the edge connecting A to B, and that's the shortest one, and the path from A to C of length 3, which is also the shortest one. Right, I mean, notice I can also get from A to C by going A to B to C, but that turns out to be longer. And in fact, for technical reasons related to how this algorithm works, which we'll see more the next lecture, I only really want to look at the direct connections between A and C anyway. Right, so let me add these labels to the graph. So I guess I'll use red. Maybe I'll circle it up here for B. And I'll label C to be 3. And what I'm going to do now is, after I've labeled my vertices in this way, I'm going to update my set S. Right, I guess so. So in order so that the step numerology is matching up, step 1 is just you initialize, you set S1 equal to A. That's step 1. Now step 2, I do the labeling I just described, and then I update S1 to S2. And so S2 is going to be S1, and I add in the closest, right? So I add in the closest vertice from my list of labels. And so I'm going to add in B in this case, right? Since B was distance 2 and C was distance 3. And so therefore I have S2 is equal to A comma B. Right? Okay, and now what we're going to do is continue this process, although at each step it gets a little bit more involved. So let me cut this over to the next page. Okay, and so now let's move on to, I just described step 2. Let's move on to step 3. So remember, we have this set S2 from the original step, which was collecting A and B together. And now what I'm going to do is update the labels, possibly adding new labels. Right? And so in this case, what I'm going to do is label every vertex that I can reach by a path through vertices in S2. Right, so I want to consider all vertices I can reach by paths that go through A or possibly B, A and B, or just A, right? So it doesn't have to include everything in S2, but I only want to look at paths that include vertices in my set S2 from the previous step. And so how am I going to label them? Well, I'm going to label according to the shortest such path. Right, so let's see how we're going to do this in this case. Well, what are the vertices that's not, right? We're only interested in vertices that are not in S2. Well, what are the vertices we can reach through via paths that go through A and B only? Well, I can reach C and I can reach D in this way, right? So I can reach C and D. So those are my candidates. And what I'm going to do is label according to the shortest possible path that I can find that only goes through vertices in S2, right? So it only can pass through A or B or both. Right, so for C, I have the direct path from A to C, which gives me a cost of 3. So this is a path of length 3. I also have a path that goes from A to B first, and then B to C. But in this case, right, this costs me 2, and then this costs me 2, so this will cost me 4. Right, and so one thing I want to point out is, well, if you look at the picture here, well, look at the labels we had from the previous step, right? So from the previous step, I have labeled C3, corresponding to the fact, well, it's the same 3 that you have here, corresponding to the fact that I knew I had a path from A to C of length 3, right? And so I really only had to, I mean, this is going to be important when we try to think about how you would program this. I really only had to check my label for C. I didn't have to look through the graph, right? I only had to check my label for C to get this. Now let's move on to updating D. Well, notice that I have a path from D to D of length 5. And then, well, if I travel along that, the quickest way to get to B from A is the label I already had previously. So that's going to be a 2, right? This 2 we have circled in red. So it costs 2 to go from A to B, and then I have a path from B to D of length 5. Right, so I can look at the path A to B to D. And so this is going to cost 7. There's also another option, right? I can get to D from C. Right, and if I go from A to C to D, well, that would cost me 6. However, I'm not allowed to look at this path, right? Because we only want to look at paths through S2, right? So in fact, I'm going to erase that, and right, this is the only option, right? And so what now I'm going to do is update the labels according to the numbers I just got, right? So D was a 7, C was a 3. Right, in fact, we already have, we've already labeled C and the label doesn't change. Now we can label D as a 7. B is still labeled 2, right? And then what I'm going to do is add the vertex with smallest label, right? So now update S2 and add the vertex with smallest label. Right, so S2 is going to be equal to, it's going to become S3, which is S2 union, right, so add the new vertex, right? So C was a 3 and D was a 7, so I'm going to add C, right? And so I'm going to get now, as my new set S3, I'll get A, B, and C. Right, and then we're going to keep doing this, right? So now I'm going to go on to step 4, and I'm going to label the remaining vertices, which are just the remaining vertices that are not in my special set S3. I'll try to update the labels according to paths that I can construct within my set of vertices, and then continue this process, right? So let's do this. So step 4. Actually, let me just go back. I mean, this is not going to be great for the printed out notes, but it's better for the video if I just stay on this page. Right, so let's now move on to step 4. I'm just going to erase this all. Right, so I haven't like eliminated all the information because we have the labels on the graph, which will help us keep track of everything. Let's just remind ourselves that S3 from the previous set was A, B, and C. And so now I want to label the remaining vertices that I can reach. By paths in S3. Right? And so what vertices can I, just by glancing, what vertices can I reach that are not in S3, which can I reach through via a path through S3? Well, I can reach D because I can just go A to B to D. So I want to label D. I can also reach Z because I have A to C to Z, right? So I can also, I can also reach Z. And so what we're going to do is look at all the options, all the possible paths that go through S3 and try to find the shortest one, and that's going to be the label, right? So what are the possible paths from A to D? Well, one thing I can do is, well, we already saw last time, if I go A to B to D, this costs 7, right? But there's another option. Now that we added C to the set, I can go A to C first and then C to D. Right, so how much does this cost? Well, notice that going from C to D costs 3. Well, going from A to C, we already knew what this was from the previous step from the label, right? So this is, let me use the same color, right? Right, so if I look at the label at C, this tells me the quickest way basically to get from A to C, which we'll prove next time, although it's clear in this picture. And so I only really, when I'm trying to calculate the quickest way to get from A to D, I already know like part of the information, right? I already know the cost to get to C, and then to get from C to D, it only costs 3, right? And so, right, so if I add those together, you'll see you get 6. And those are the only, we just looked at all the possible ways to get from A to D, as long as I stay inside S3. And so the label for D is going to be 6, which is the smallest of the two. Now you may be confused, like why I just digressed for a minute to talk about the fact that we knew that the distance from A to 3 was C by looking at the label. For this example, you don't have to do that, right? Because it's just very clear. You can just see very quickly. It's going to turn out, though, that the way this algorithm works, maybe C is not going to be at some step, maybe your vertex C is not going to be directly connected to A, and maybe there's some like large portion of the graph that you have to travel through to get from A to C. What this algorithm is going to do, though, via these labels, is keep track of the shortest way to get from A to C. So that when you reach this point, you don't have to look through the whole graph again. You just have to look at the label you have on C, and that tells you the length of the shortest path from A to C. And therefore, if you're going from A to D through C, you already know like the part of the length of the shortest path, right? So it's sort of, again, like a sub-problem that's being built into the larger problem that we're solving as we go along, right? We're solving the shortest path from A to C, which will help us find the shortest path from A to D, which will then help us find the shortest path from A to Z. Right, so that's the idea of how this works. Right, so now we update the label D. Now D becomes a 6 instead of a 7. Right, so let me change this to a 6. And now let's finally look at what can happen with Z. Well, I can get to Z through S3 in only one way, right? Because if I have a path from A to Z, it has to go through either D or C. And since D is not in my set S3, I'm only looking at the path that goes through C. And so that's going to be, well, I have A to C to Z. Once again, either from directly inspecting or by looking at the label, this length is 3, the length from A to C. And then the length from C to Z is 2. And so that's going to be a label 5. Right? So we're going to label Z a 5. And then as we did before, we're going to update the set S, right? So now I'm going to have S4, which is S3 union, the vertex with the smallest label. In this case, Z has the smallest label. So I'm going to add Z, right? And so S4 is going to be A, B, C, and Z. And so now I'm going to claim that we're done. And so the claim is the algorithm, well, this is not a claim, this is just the definition of how the algorithm works. So the algorithm terminates once you add Z to the set. So once Z is added to Si for some I. And then the theorem, which is like the theorem that says this algorithm works, is that the label of Z at this step, like once Z is added to Si, is the length of the shortest path. right? And moreover, you don't just know the length of the shortest path. I mean, if you trace back what we did, you'll actually be able to use this algorithm to find the path, right? Not just find the length of it, but to find what the path was, right? Right, and so that's basically what I wanted to talk about for today. Right, so if again, this may seem overly complicated because if I just gave you this picture and I asked you to find the shortest path from A to C, you could do it in a minute or two just by listing out the possibilities. But what we'll do next time is make this work for much more complicated graphs. It's going to be the same exact process. So if you understand this argument, then you'll be able to understand how it works for graphs, not just of 6 vertices, but with, or not just 5 vertices, but with like 100 vertices or something like that. And then I'll say a little bit about how the proof works in the next lecture. And I think what I'll do additionally is send you a detailed PDF with the proof written out in detail as well. Just because it may take more than a full lecture to go through the proof in detail if I want to be careful. And I don't think that the argument that's written out in the book is very, very clear. So I wanted to expand on it a little bit, but we have to take into account time issues. So I may send you a PDF write-up of the proof instead of going through it all in the lecture, but I'll think about that over the next day or so. Right.